Hello everyone, this is 10.3 polar coordinates, and in this section we'll basically be talking about what polar coordinates is and how you would graph something in polar versus graphing in Cartesian, how you can actually translate between these two, and then we'll also be talking a little bit about the calculus of polar coordinates. We'll talk more about calculus in 10.4, but there will still be some calculus spoken of here. So the first thing I want to discuss is what polar coordinates mean. So Cartesian, what we kind of know and love, is of the form x comma y. So every point is of the form x comma y. It's x coordinate comma its y coordinate. This is known as rectangular coordinate sometimes because it creates a nice rectangle like that. Now polar coordinates, however, will have the radius first, which is essentially the distance from the origin, and the angle second. And this is the angle from the positive x-axis, kind of like how you do for the unit circle. So this is the angle coming from here going in a counterclockwise fashion. If it's a negative angle, like we'll see in this example, you go in the clockwise orientation. R is the distance from the origin. So the way you plot a point, instead of going to the x value and the y value, you go out a certain distance and move a certain angle. So if you want to move that angle first, so let's say the angle is 180, then you go travel 180 degrees and then move along whatever your radius is. Or you can move the radius first and then the angle after. It doesn't really matter which one you do first. Kind of like here, do you go over and up first or do you go up and over first? Doesn't matter, you still arrive at this point. So I'll do a few examples of plotting, and then after this, then we'll talk about the relationship between the two. So here we have our r theta points. So let me just label these. And I will actually plot both of these on the same xy plane. And notice they're both on the same xy plane for polar and Cartesian. And it'll be nice to find out what our points result in Cartesian. So I actually will discuss that. But then, like I said, after this, we'll see the actual relationship in general between polar and Cartesian. There's a nice formula. There's a few formulas in actuality. But let's see. So for the first one, here's what we're going to do. So the angle is 3 pi over 2, which, if you don't remember, 3 pi over 2 is, maybe I'll convert these to degrees so it's easier for us, but pi over 2 is 90. Remember that pi is equal to 180 degrees, so let me write that. Pi radians is 180 degrees. So anytime you see pi, if you were to replace it with 180 degrees and then do the math from there, that's a quick way of converting. So I see this and I think 180 over 2 is 90, and 90 times 3 is 270, so that's right down here. So if we travel 3 pi over 2 radians, that'll lead us down here to the negative y-axis, and then travel a distance of 2, 1, 2, that'll leave us at this point, which is 0 comma negative 2. So this actually corresponds to the Cartesian point 0 comma negative 2. Okay, here pi over 4, well 180 over 4 is 90 over 2, which is 45. So this is an angle of 45 and a distance of radical 2. So we're first going to travel a distance of radical 2. Which is, well, somewhere over here. This is radical 2, and then we're going to swing this up by 45 degrees. So we'll actually land here at 1, 1. Let me plot it in red, I guess. Doesn't really matter. And how I know it's 1, 1 is because if you had a triangle, a right triangle of sides 1 and 1, well, by Pythagorean theorem, the hypotenuse has to have a distance of radical 2. So let me just denote here that this red line distance is the square root of 2. So the Cartesian point that this point corresponds to is 1 comma 1, actually. Okay, this is interesting because they're both negative for the third point here. So we're going to first travel pi over 6. 180 over 6 is 30 degrees, so I'm going to travel 30 degrees. And in the opposite direction, so it's a negative negative angles, so we're gonna not go counterclockwise like usual, we're gonna go clockwise. So we're first going to, let me do this. In red here, I'm going to make this line. And this dashed line here will represent the angle of negative pi over 6. Theta equals negative pi over 6. Okay? So if I move down this angle and then go a radius of 1 on this line, then we'll arrive at a point. But since it says negative 1, what does that mean? Well, instead of going toward that, well, in that direction basically, going out, you go inward. So it actually will go back to this direction a distance of 1. So here, this distance, imagine this is 1. So whatever this point corresponds to, which isn't very obvious, but at least we can see what quadrant it's in. Okay, the one more thing I guess I should say though, is that notice this point here, it's kind of hard to draw because the image gets a little cluttered obviously, but this point here, well notice we traveled a radius of negative 1 and a angle of negative pi over 6. So going in this direction from the positive x-axis gives us a negative angle, but if we went in this direction, well, what's the angle? Well, here, the angle is 30 degrees, or pi over 6, because of symmetry, basically. So then this angle here will be 150 degrees, which is actually 5 pi over 6. So this point actually is the same as 1 comma 5 pi over 6. And as it turns out, that's something very interesting with polar coordinates. There are multiple ways of representing a point. And in fact, there are, well, infinitely many ways of doing it actually. But you can always do that. If you wanted to change a radius to negative or vice versa, you just add or subtract 180 degrees and it ends up being the same thing. If you wanted to change a angle to negative or to positive, if it was negative, you add 360 degrees because that'll make it positive now. So if we add 2 pi, which is 360 to negative pi over 6, it would be 11 pi over 6, which corresponds to this line here, if you travel like that, down here in the fourth quadrant. But if you add 180, which is pi, well, adding pi to negative pi over 6 is 5 pi over 6, which is up here now in the second quadrant. And yeah, we're adding 180 to that, and as a consequence, the radius will change from negative to positive. So that's a nice consequence that I'll try to generalize right now. So I'm going to try to do that as well as discuss those relationships between polar and Cartesian. So let's take a look. All right, so here let's recall that for a point r theta, we can always write it in Cartesian as x comma y. So this is what we have basically in the general case. So the angle is theta, the radius is r. Here this is in the first quadrant, but in fact this image is kind of true no matter what quadrant you're in. You'll just kind of have to interpret it for different quadrants specifically, I guess, but what I'm about to say will actually hold true for no matter which quadrant you're in. So if you consider this right triangle, there's a couple things you'll notice right away. The first thing I think that everyone should notice is by Pythagorean theorem, x squared plus y squared is equal to r squared. All right? The next thing that you should probably notice is that, well, to get theta involved, you can use, well, sine and cosine. So if you do that, what is, let's do sine first. So if you take sine of theta, you'll get y over r. So multiplying by r, you will get y is equal to r times sine of theta. Similarly, if you were to take cosine of theta, that'll be x over r. Multiplying by r will give you x is equal to r times cosine of theta. Just like that. Now, of course, if you wanted to take tangent, well, tangent doesn't even involve r. Tangent of theta is y over x. So let me just write that here. Equals y over x. and you can actually use this to find the angle. So for the most part, this is really used to find theta, because what you can say from this is that theta is equal to tangent inverse of y over x. You have to be kind of careful when you do this, because you need to make sure that you're in the right quadrant and you find theta correctly. Because of course, if you recall from trigonometry, the inverse tangent function only has well, I guess a range negative pi over 2 to pi over 2. So you have to be kind of careful with this one when you find the angle, if you were to use it like that. In fact, if you were to square root to get r by itself, you get r is equal to the square root of x squared plus y squared. I would say plus or minus, but if you take it to be a positive radius, then it's just a positive one. But we have seen we could get negative radii. So in fact, maybe let me just include that just to play it safe, plus or minus. But to be quite honest, the ones I want to mainly focus on are these two. So let me just say this. These are used to convert to Cartesian. But to convert to polar, you would use this one and this one. And I think that makes sense, because if you have an equation in Cartesian, you want to get rid of x and y, and you want to find r and theta. And these two formulas that I have circled will find r and theta given x and y. However, if you want to convert to Cartesian, well, these two will take r and theta and output x and y. So I'm going to do a few examples here where I want to convert these polar equations to Cartesian so we can see what they actually signify. So here, of course, r squared is equal to x squared plus y squared. So x squared plus y squared replaces r squared, and it's 5. So what this actually is a circle of radius radical 5, which is kind of nice to see, centered at the origin. So even though, r squared equals 5 is not super meaningful to us, in fact, if you square root, you get r is equal to plus or minus the square root of 5, which means it's the set of all points whose radius from the origin or distance from the origin is the square root of 5, positive or negative. So that actually also corresponds to a circle of radical 5. Here, well, we have cosine of theta, but we want r cosine of theta to make it an x. So if we multiply both sides by r, so this is the answer for the first part. But for the second part, if we multiply both sides by r, we'll get r squared on the left, but on the right we'll get 5r cosine of theta. And that's good because what's r cosine? R cosine is x. And r squared is what? Like we saw from the previous example, it's x squared plus y squared. So this will turn into x squared plus y squared is equal to 5x. Which I kind of want to leave like that. This is also a circle, as it turns out. If you subtract 5x to the other side, you'd have to add a number to both sides to complete the square for x. And basically, it's a circle with a different center. By the way, in your graphing calculator, there's a mode for polar. So if you press mode, you can translate between, there is Cartesian, polar, I believe it says function for the TI-83s. There's function, polar, there's even parametric, and there's a sequence, which we'll use in a later section. There's also, when you press mode, there's two options for radians or for degrees. So make sure you're in the right mode when you're calculating or evaluating sine or cosine or any trig function of a given angle. Make sure you're in either radians or degrees, depending how you take it. Here, this is kind of weird because it's of 2 theta. How can we get rid of the 2 theta? We can use a double angle formula. Now, for cosine of 2 theta, there's like 3 different versions of that. So whichever one you want to use, we can use either one of those. That's going to be a little tricky because they involve squares. But I think that's going to be okay. In fact, I'm going to do this. I'm going to say that cosine of 2 theta is cosine squared of theta minus sine squared of theta. And that's one of the 3 versions of the double angle formula for cosine. In fact, that's like the first one people normally learn. If you distribute this r squared, you get r squared cosine squared minus r squared sine squared equals 1. Now, r squared cosine squared is just r cosine all squared, which is x squared. Similarly, r squared sine squared is y squared. So this is x squared minus y squared is equal to 1. And if you recall from conic sections, which we didn't learn in this class, but we'll actually discuss conic sections. So if you haven't seen conic sections, you probably should have. But if you, that's okay though if you haven't. But if you don't recall it or whatever the case may be, we'll see that actually in 10.5, I believe. But this is actually a hyperbola. It's a horizontal hyperbola actually. But in any event, I want to talk a little bit about specific types of polar graphs, and then from there we'll see some calculus involving polar coordinates. So let's take a look. So there's all sorts of weird, different, funky graphs you get when you plot things in polar. So it's nice to play around with that with your graphing calculator. So if you make sure, again, you're in polar mode when you press mode, and then when you press y equals, it'll say r equals instead of y equals on your calculator, and then you can, when you press that x button that's next to alpha, it'll say theta instead. So that you can plot these to kind of see, and you can mess around with them a little bit to get different images, and you get all sorts of weird, wacky things. And if you follow through the book, they kind of show some transformations that are nice too. I don't want to talk too much about it, but I'm just going to show you the different types. These are the 4 main types that I think are the more common ones. This here is known as a cardioid. I guess because it kind of represents a heart to some extent, I guess. So that's 1 plus sine of theta. So if you graph that, you'll get this. If you follow through with actually, so that's one thing I'm not doing here, but if you follow through with actually graphing this by hand, basically what you have to do is you start with theta equals 0, and then when you plug that in, you get a certain radius, and then you take that as far as you need until you get back to wrapping around, basically. Sometimes you don't need to go to just 360 degrees. You may need to go further or less. Like in this case, if you were to go to 360 degrees, when you plug that in, you get to cosine of of 720 degrees, and it wraps around kind of quickly. But it just depends on what the equation is. You don't always have to go all the way around from 0 to 2 pi or 360. Sometimes you need to go more or less. It just kind of depends. But anyways, this shape is called a cardioid. This shape is called a rose. In particular, this is a 4-leaved rose. It doesn't really look like a rose, but that's just what it's called in mathematical terms. And this, of course, is a circle. So r equals a number, like I mentioned earlier, is just a circle of that radius, whatever the number is, and is centered at the origin. If you want a different center, then the equation will look a little different. In fact, there's something you can do with the cardioid to make it be a circle centered up here, so that part of the circle hits the origin. And I'm not going to show that, but it's kind of nice to see the different transformation of that. And it basically has to do with changing some multiplier of sine, I believe. But anyways, you can play around with that. And then, of course, finally here for the 4th one, we just have a line. And this is when you have theta equals something opposed to r equals something. Because here, everything on this line at the angle pi over 4, which by the way is just the line y equals x, will have that angle. So every point here, no matter what the radius is, will have this angle pi over 4. So if you plotted a point, what you have to do is travel that angle and then go out that radius. So independent of what the radius is, this is the angle. Kind of like here, whatever the angle is, it doesn't matter what the angle is, independent of the angle, the radius is too. So that's kind of neat that we can see that. So again, yeah, just different interpretations of how to graph things opposed to the way we're kind of used to. But, it's just one little thing I wanted to show, the specific types of graphs. Now we're going to take a look at the calculus in polar coordinates, so let's see that right now. All right, so here finally for the calculus of polar coordinates, we're going to take a look at tangents to polar curves. And really what we want to find for tangents, remember, is just dy over dx. Now remember that for 10.2, we saw tangents of parametric, then we took a look at areas, and then arc lengths. We saw surface area, but we didn't do any example of those. And actually for areas and arc lengths for polar curves, we'll be taking a look at that in 10.4. So this is really where 10.3 is going to end in just finding derivatives, basically. We're not even going to do second derivatives because it gets way too crazy, as you might imagine. Basically what I'm going to do here is to find a formula for dy dx. It's going to be the same way we did it for parametric, but since our equations are different, we get different results. So here we have dr d theta over, well, dy d theta, there we go, over dx d theta. So imagine theta is t, so this is what we did for parametric. We just took top and bottom and took that over dt, but here it's d theta instead. And our equations, by the way, are the following. X is equal to r cosine theta, and y is equal to r sine theta. Now, it gets a little funny because if you take the derivatives of each of, we don't need parentheses, I guess, but if you take derivatives of each of these to find dy d theta and dx d theta, if you take the derivative with respect to theta, since r is a function of theta, because usually it's r equals something in terms of theta like we have here and here, you have to use the chain rule. In fact, you have to use the product rule. So I'm going to actually show you what they are here. So for dy d theta, if you take the derivative of r sine and follow the chain rule with the product rule, you get the following. I guess it's mostly following the product rule. It's not so much chain rule, but you get the following. So derivative of the first, derivative of r is dr d theta, times regular of the second, which is sine, plus regular of the first, r, times derivative of the second, derivative of sine is cosine. Okay? Very similar for dx d theta. Again, product rule. Derivative of the first, derivative of r is dr d theta, regular of the second, cosine, plus regular of the first, r, times derivative of the second. Derivative of cosine is negative sine, so I'll change this to negative. There we go. And this is it, actually. This is the formula for finding the slope of the tangent line. At a given point, then you plug in the values. In this case, you probably plug in theta, and it's no mistake here that we're going to plug in theta, and we're given a theta value. So we'll do that here for this example. Find the slope of the tangent line at a given value of theta. So let's see. So we want to find dy dx. And we just found out how to do that. So we need dr d theta. So derivative of r with respect to theta is whatever derivative of this is. So derivative of 2 cosine theta is negative 2 sine of theta. Okay, and I'm just going to follow this. So that's that times sine. So that times sine will end up being sine squared. So I'll just write that if that's okay. Plus r times cosine. Remember, r here is 2 cosine. So 2 cosine times cosine will be 2 cosine squared. Over dr d theta, again, is derivative of r in this case is negative 2 sine, times cosine is negative 2 sine theta cosine theta. Okay, minus r, which here is 2 cosine, times sine is 2 sine 2 cosine. So the cosine part, it comes from r, of course, and the sine part came from the formula. Well, anyways, these two definitely combine. They combine to negative 4 sine cosine. So I'll do that. So let me erase this. They combine to negative 4 sine theta times cosine theta. So I'm not showing too much work here, but hopefully we can follow. And now we want to evaluate this now at theta equals whatever the value was given, and that's pi over 3. So now we're going to plug in theta equals pi over 3, and let's see what we get. All right, well, again, up on top, and there's probably more cancellation you can do to simplify this expression. The one I see right away is divide everything by 2, but that's okay. Plug in pi over 3, we get negative 2. Sine of pi over 3 is radical 3 over 2, so that's radical 3 over 2 squared, plus 2 times cosine of pi over 3 is 1/2, so that's 1/2 squared, over negative 4, sine of pi over 3 is radical 3 over 2, cosine of pi over 3 is 1/2. So when you actually evaluate this, we kind of separate these. What do you get? Well, let's see, I don't have too much space, but up on top, I get negative 2 times, if you square this, you get 3 over 4. 2 times 3 over 4 is just 3 over 2, so that's negative 3 over 2. Plus, well, 1/2 squared is 1/4 times 2 is 2 over 4, which is 1 over 2. So negative 3 over 2 plus 1 over 2 is just negative 2 over 2, which is negative 1 up on top. So on the top we have negative 1. That's what that simplifies to. On the bottom here, this is all over 4, so this 4 cancels these two, and we just get negative radical 3. So negative 1 over negative radical 3. And of course you can write this as radical 3 over 3 by rationalizing. And it is positive again just because, well, negative over negative is positive. So that was it for the first one, so that's kind of nice. Now the second one here, well, let's see if we can follow it in the same way. I know it's kind of cluttered, but let's see what happens. So we have dy over dx, and then we're going to plug in theta equals pi. Now again, following this formula, we have this pretty long fraction, I think. dr d theta, derivative of 1 over theta. Well, 1 over theta is, let me write it over here. 1 over theta is theta to the negative 1, and its derivative is negative theta to the negative 2. So a way of writing this is negative 1 over theta squared. So it's negative 1 over theta squared. So these dr d thetas will become a negative theta squared in the bottom. Everything else will stay the same for the first terms. So up on top, this will be negative sine over theta squared, like that. And the first term on the bottom will be negative cosine over theta squared. So I hope we can see how I got that. And now r, well, r is just 1 over theta, so the second terms will be over theta instead of over theta squared. And they're not negative. Well, the signs will follow these. The signs won't change, basically. So we get plus cosine over theta minus sine over theta. Again, I'm kind of skipping a little bit of detail here, and then we're going to evaluate it at theta equals pi, of course. But I don't think it's too bad to follow. But you can try to work at the details on your own. And these may simplify. In fact, if you multiply top and bottom by theta squared, we get a lot of simplification. But I'm just going to leave it like that and just plug in pi and see what we get. So on top, I'm getting sine of pi is 0, so that's just 0, over pi squared, but it's still 0. Cosine of pi is negative 1, so it's going to be negative 1 over pi, because the top's negative 1 and bottom's pi. Here in the denominator we get negative 1, because cosine of pi is negative 1, over pi squared. So that's going to be double negative, so it's positive 1 over pi squared. And sine of pi is 0, so that's minus 0. So this all together is negative 1 over pi over positive 1 over pi squared. Now if you multiply top by the reciprocal of the bottom, you get negative 1 over pi times pi squared over 1. And this is just negative pi in total. So that's our answer there. So there's cancellation basically of the powers, like that. And again, the double negative made this positive on the bottom, but the top was still negative. Nice. So again, that's all I wanted to see as far as tangents go for 10.3. If you wanted to find a horizontal tangent line or a vertical tangent line, you would check to see where the top is 0 or where the bottom is 0. I say that because there are some homework problems that ask that, but it's really just doing this and then setting the top equals 0 to make it horizontal, or the bottom equals 0 to make it a vertical tangent line, because it's where the slope would be undefined versus where it would be 0. So kind of keep that in mind for those. They're not too bad though. This, I think, was probably the hardest of those. It's just using this formulation and then plugging in a value. So thanks for watching. Hope you enjoyed it, and I'll see you in the next video for 10.4. See you then.